Hi, so let's go through some properties of determinants, okay? So if you've been following my lessons, you've started talking about matrices and now you're on the determinant function, and we've talked about how to find the determinant using cofactor expansion, and that's the formal definition of determinants. And now we are on properties of determinants, okay? So if A is a square matrix, so if you have a square matrix that contains a row or column with zeros entries, then the determinant of A is equal to 0. If you have a full column or maybe one column full of zeros in it, like this example here, then the determinant, if I try to do my cofactor expansion along the column 1, the determinant of A is equal to 0 times some determinant of a remaining matrix plus, so that is using this 0 plus 0 times determinant of some other, right, plus this 0 times the cofactor expansion of the 0 at the last one that will multiply a determinant of something. Ideally there's supposed to be a negative 1 in front of these, maybe negative 1 to the power 1 plus 1, but negative 1 times 0 is still 0. That's why I still have the 0 there. So in all, you have each term here being multiplied by 0, so everything here will be 0. Likewise, this one. Okay, so if you do the same thing to the other one, you have 0 as well. Now, if you have a square matrix A, and then the matrix is in its upper triangular matrix or lower triangular matrix, so whether the or maybe it's a diagonal matrix, so all that you're looking for is that if the matrix is a triangular matrix, being an upper, lower, or diagonal matrix, then the determinant of that matrix is the product of the diagonal elements. Okay, so here if I pick this matrix A, then determinant of A here is equal to the product 1 times 5 times 4, right? And this is equal to 20. You don't need to really go through cofactor expansion and the rest, okay? If you choose this last row here and use cofactor expansion there, that will give you a faster way of finding it. Now with the matrix B, determinant of B, this is a 2 by 2 matrix and it's a lower triangular matrix. Okay, it's equal to negative 5 times 6, and this is equal to negative 30. Now if you pick this matrix C, it is a diagonal matrix, so determinant of C is equal to 10 times 5 times negative 3, and that's going to give you negative 150, right? So that is the properties when you have a matrix being a triangular matrix, either a diagonal or upper triangular or maybe lower triangular matrix. Now if you have a square matrix n by n, then I'm going to talk about three things. So if B is the matrix that results when a single row of A is multiplied by a constant k, then the determinant of B is equal to k, the constant, times determinant of A. What this means is that I have this matrix A here. If you look at the matrix B, look at it very carefully, you realize that B is being formed when you multiply the row 1 of A. So row 1 of A is the elements 2, 1, 2, 3. If I multiply them by 4, I'm going to get 4 times 1, which will give me 4, 8, and then 12. So you realize that the first row of A is being multiplied by a constant 4 to get the matrix B. Other rows are the same, right? So this is happening in a row. If it happens in a column 2, that will be the same thing. Then the determinant of A, if I'm to do this step by step, the determinant of this matrix A here, determinant of A is negative 2. If you do it step by step, you're going through process of finding the determinant of a matrix. Okay, so you can do it. And then on the other hand, the determinant of this B, I want you to verify that the determinant of B is equal to 4 times the determinant of this A. Negative 8, sorry. So what this means was that once you know the determinant of the original matrix, and you know that this matrix is being formed by multiplying one row, that is the row 1, by 4, the determinant of this matrix B is that same constant you multiply to that row by the determinant of the original matrix. Okay, so you have negative 8. This makes sense because if you do the cofactor expansion of B, the matrix B, along the first row, that would just easily come out. Now the 3b is that if B is a matrix that resolves, so we are still basing on this statement that A is a square matrix, and I'm forming a new matrix B from A, with the result when two rows of A are interchanged. I mean, the same thing applies to sorry, the same thing applies to when you interchange two columns. Okay, then the determinant of B is equal to negative determinant of A. So the same matrix we just did, we know the determinant of this is negative 2. If you compare matrix A and B, you realize that the row 1 and then row 3, just look at them very carefully. I mean, it's actually row 1 and row 2. Right? If you look at it very carefully, they were swapped. Okay, so we swapped them, and then we formed this matrix B. So once we've done that, then it means that the determinant of this matrix B is equal to the negative of the determinant of A, which is 2. And like I said, if you do the cofactor expansion of this, I mean, if you find the determinant using the cofactor expansion, you're going to get 2. Right? So these are properties you should know. Now, on the third one from the C, if B is a matrix that resolves when a multiple of one row of A is added to another row of B of A, and the determinant of B is determinant of A. What it means is that, I mean, at some point I'm going to do how to find the determinant of a matrix using row reduction method, okay, or maybe elementary row operation. So if you are doing that and you multiply some constant to maybe one of the rows of A and add it to another row, I mean, all these things I'm talking about also happens for the same thing happens when you use columns, okay? The determinant of A and B will be the same. So if you look at the first row of A is 1, 2, 3, first row of B is 1, 2, 3. Last row of B is 1, 2, 1. I mean 1, 2, 1, this is 1, 2, 1. But if you look at B, the second row of B is the same thing as saying that if I multiply negative 2 times row 3 of A plus the same row 2 of A. So if I multiply negative 2 by this row, I'm going to get negative 2 here, plus 0 will give me negative 2. If I multiply it here, I'm going to get negative 4 plus 1 is going to give me negative 3. Negative 2 times this is going to give negative 2 plus 4 is going to give me 2. So you realize that B is formed by multiplying negative 2 to row 3 of A and then add it to row 2 of A. So we change that to this form and form a different matrix. And what this whole thing is saying is that then the determinant of A should be equal to the determinant of B. And we know that determinant of A is negative 2, so the determinant of B is also negative 2. And in all these, what I'm trying to say is I try to confirm these by just taking your time to find the determinant, okay? Now the fourth property is that if A is a square matrix, then the determinant of A transpose is equal to the determinant of A, or determinant of A is equal to determinant of A transpose. This I'm going to use a very simple matrix, that is a 2 by 2 matrix. Here the determinant of A of a 2 by 2 matrix is 1 times 5 minus 3 times 2, and that is 5 minus 6, which is negative 1. Now A transpose is writing the columns of A as rows, right? And then if I find the determinant of this, I mean, this is the same thing as 1 times 5, determinant of A transpose is equal to 1 times 5 minus 2 times 3. And this is the same thing as 5 minus 6, which is negative 1. So that's the property, that the determinant of A and H transpose, both of them have the same determinant. Now if you have a constant multiplying K A, so if you have KA, and you know the determinant of the matrix, original matrix A, then the determinant of Ka is equal to K to the n times determinant of A. I mean, these properties are very important here. So I know the determinant of A in this matrix is 3 times 2 minus 2 times 1, which is 6 minus 2, and that is 4. So this is a 2 by 2 matrix, right? This n here is a dimension of your matrix. This is a 2 by 2 matrix. So n here in this case, n is equal to 2. And 5 times A means multiplying each element or each entry in A by 5. So what this property is saying that the determinant of 5a should be equal to 5 to the power of the dimension, which is 2, times the determinant of a, which is 4. So it's going to be 25 times 4, that is 100. Now if you look at this, the determinant is 15 times 10, which is 150, minus 5 times 10, which is 50, and that's going to give me 100. Okay, so these two have the same determinant. And that is what the property is saying, that if you have a scalar multiplying each entry of a, then the determinant of the scalar multiple of the matrix is equal to the scalar to the power of the dimension times the determinant of the original matrix. Okay. The sixth property is saying that if two rows of a or columns are proportional, then the determinant of a is equal to 0. Now, if you look at what this is saying, is that if I have two rows, let me pick this a. That of a should be 0, and the reason is because if you look at the column 1 is 1, negative 4, 2. Look at column 2, which is negative 2, 8, negative 4. If you look at this very carefully, this is column 1, C1, this is C2. Realize C2 is equal to 2 times, or negative 2 times C1. So they are in proportion, right? One is equal to the other. And then the whole thing is that if I find the determinant of this using cofactor expansion, I should get 0 because of this property. Okay, so what is this whole thing is trying to tell us is that we should, if it happens for rows as well, then the determinant should be 0. So if you have one row of a matrix being the same thing as another row, they are proportional, of course, because if you have C1 equals C2, they are proportional in the sense that one is just 1 times the other, right? So you're going to get the determinant to be 0. So, I'll urge you to do this by yourself. You can do it. Now, if a and b are of the same size, then the determinant of ab is equal to determinant of a times determinant of b. This side is very, very crucial because it involves a lot, and this property of determinant is being used to find to prove a lot of theorems in linear algebra. Okay, so determinant of a in this problem is equal to 3 minus 2, which is 1, and the determinant of b in this one is equal to negative 8 minus 15, and that is what was that? This is question 4. So negative 8 minus 15 is actually negative 23, right? So you have negative 23, and then if you look at the determinant of AB, what this property is saying is that we should have the determinant of A times the determinant of B, and that is negative 23. Now, on the other hand, too, if you look at this very carefully, you can try to find the determinant of this, which is 2 times 14, which is 28, minus 3 times 17. I don't do that yet, but you can try to find out. So 28 minus 3 times 17, and it's like 45 plus 6, right? So I don't know if that is right, but this is 51. Yeah, that should give me negative 23. That is what I think it should be, so you can try to do that. But this is a very crucial property. Now, you're going to use that property to prove that if A is invertible, then the determinant of A inverse is equal to 1 over determinant of A. Now, if A is invertible, we've done invertibility of matrices and then inverses of matrices, right? So, if A is invertible, then A times its inverse is equal to I, the identity matrix, right? And so I'm going to find the determinant of this whole different side, determinant of I. Now remember that I is just a diagonal matrix with ones at the diagonals. So the determinant of that is just a product of the diagonal entries, and the diagonal entries are all ones. So I'm going to get 1 here. And the determinant of A inverse is using properties of determinant. We're going to have this. And so the determinant of A inverse will follow from this part, that this is equal to that. Right, and then there's a consequence of this, that if A is invertible, then the determinant of A shouldn't be 0, and then if the determinant of A is not 0, then the A is invertible. So this is a statement resulting from this part that A is invertible if and only if a determinant is not 0, because if the determinant is 0, then we cannot have a determinant for the A inverse. If A is invertible, we can have A inverse. And then if the determinant of A is 0, then the determinant of A inverse is 1 over 0, which does not exist. So this wouldn't work if A is not invertible. So what this whole thing is saying is that A is invertible if and only if the determinant of A is not 0. Alright, so you're going to take, like I said, you're going to work on how to use elementary row operation to find the determinant of a matrix. Stay tuned and don't forget to subscribe to my channel if you have not subscribed. See you next time.